first topic will be introduction to lasers and their role in manufacturing. Will be presented, like I said, by Florian Lull from Fraunhofer IWS. And just to present our speaker, so Florian Lull study laser technology with a focus on laser material processing at University of Applied Science, MIT-WADA. I don't know if this is the right way to say it. He is employed in Fraunhofer IWS, as I said, in the laser precision processing working group since 2019. His expertise is micro material processing, ultra short pulse lasers, and also system technology development. So, Florian, thank you to be here today. I hope that this was a good introduction to yourself, but you can add anything that you might want to share with us. So I already see your screen. I think you can go for your
Perfect.
presentation. And thank you again.
Okay, thank you for this kind introduction. I think everything about me is said, so we can dive right in. What I try to do today, now it works. What I try to do in my presentation is to give you an overview on the fundamentals of laser technology, how a laser works, what are the special properties of laser radiation we can use, what happens when the laser radiation hits a material, and last but not least, some typical laser applications. And we will start with a very simplified model of an atom, of the electronic system of an atom. What you can see here is the ground state. Laser pointer. This is the ground state. This is basically the energetically state where the electron is in its energetically equilibrium, and we have an elevated energy state where the electron is when it has more energy than in the ground state. So now a photon comes flying by, is absorbed by the electron. The electron has now more energy and is moved to its higher elevated state. And this process is, of course, called absorption. On the other hand, the process, we have an electron in the elevated state. The electron is falling down into its ground state. By falling down, a photon is emitted, and this process is called spontaneous emission because this happens randomly. If we combine those two processes, so we have an electron in an elevated state, plus a photon is flying by, the electron is stimulated to fall down in its ground state, and the second photon is therefore emitted. We call this process stimulated emission, and this process of stimulated emission is extremely important for the laser principle, because those two photons are exact copies of each other. So they have the same wavelengths, they have the same direction of propagation, they have the same phase, and they have the same polarization. And in fact, the stimulated emission is also part of the name of laser, because laser just means light amplification by stimulated emission of radiation. Okay, so all of these three processes happen inside of the so-called laser active medium, which is just a special material, could be a solid, could be a gas. And we have to bring energy inside of the laser active medium by so-called pumping. This pump energy can be electrical energy, can be optical energy. And by pumping the laser active medium, we bring a lot of electrons in their elevated state. Then in the next stage, all those electrons with a lot of energy fall down in their ground state. A lot of photons are randomly spontaneous emitted. So you can see a lot of photons are emitted with different directions of propagation. And to create out of this laser active medium, this glowing laser active medium, a laser, we need two mirrors. We need a 100% reflective end mirror, and we need a partly transmissive output mirror. And those mirrors together form the so-called laser resonator. And what those mirrors do is they reduce the optical field, um, and only those photons which are parallel to the optical axis of the system are reflected at the mirrors, can be reflected back into the laser active medium, where they can generate more photons, in this case by stimulated emission. So the combination of laser active medium, pump energy, and two mirrors forms the basic principle of a laser. And we get laser radiation inside of the resonator, and a part of this laser radiation is then transmitted through the output mirror, and this is the beam we can use for material processing. Due to this special principle, laser radiation has some special properties, and we start by comparing the laser radiation to some ordinary sources of radiation, for example, a light bulb or the sun. And I think you can imagine that for the sun, for example, the photons are emitted in many different directions. So the power density, basically the photon density, is decreasing with increasing distance from the light source. And this kind of radiation is called high divergence radiations. On the other hand, we have the laser. The laser has a collimated, almost parallel radiation due to the to mirrors, and therefore the power density is nearly independent from the distance from the laser source. So a laser has a low divergence radiation. Again, um, natural light source, the sun, has a broad spectrum of wavelengths which is emitted. So you can see we have wavelengths in the UV part of the spectrum, we have wavelengths in the visible part of the spectrum, and even in the infrared part of the spectrum. And a laser, on the other hand, has just one single wavelength. And to give you an idea how many laser wavelengths and therefore laser types exists, you can have a look at this graphic. And to bring it down to the most important types of lasers, we start with the CO2 laser. This was the laser which was in the 60s and 70s and 80s the first laser used in material processing, because it was the first lasers with sufficient power levels. Because it has some certain disadvantages. In the 80s and 90s, the CO2 laser was more or less removed from the industrial world by the neodymium YAG laser with a wavelength of 1064 nanometers. So this is right now the most important laser for many parts of the laser industry, like cutting and welding and so on. The next laser, helium neon, with a really nice red color, 632 nanometers. This is a typical measurement laser. The Titan Sapphire laser is a laser with actually not one wavelength, but a wavelength spectrum. And this was the first laser which could produce ultra short laser pulses. So this is a typical laser for fun. And last but not least, some lasers which many of you probably have used without knowing, those are the laser diodes used in DVD and Blu-ray players. Okay, so now we have to look at the time regime of lasers. And in the time regime, we can differentiate between two classes of lasers. We have the CW laser. CW stands for continuous wave laser, and we have the pulsed lasers. So continuous wave, um, as the name says, we turn on the laser, it emits continuously laser power, we turn the laser off, and the power stops. So in this case, the average power is similar to the continuous power. For pulsed lasers, we need a few more characteristics, values to describe this laser radiation. Um, the pulsed laser radiation is characterized by the pulse repetition rate, basically how many laser pulses are emitted by the laser per second. It is characterized by the pulse energy. You can think of this like how many photons are in one laser pulse. With pulse repetition frequency and pulse energy, we can calculate the average power of a pulsed laser system. And maybe the most important um, value of pulsed laser radiation is the pulse duration. With pulse energy and pulse duration, you can calculate the peak power. And here you can see that by decreasing the pulse duration, you can increase the peak power. So for pulsed lasers, it's generally true that the peak power is much, much higher than the average power. And to go even a step further, we have to talk about the peak intensity, which is just peak power divided by a certain area. And this area is in most cases the cross section of the laser beam, of a focused laser beam. And the intensity basically describes how the interaction between laser radiation and material happens. So if we have a look at the table on the right side, you can see that from going from nanosecond laser pulses to picosecond and femtosecond laser pulses, the peak intensity is increasing by a lot, orders of magnitude. And to give you an idea, here are some intensities, everyday intensities, I like to say. So the intensity of light inside of your eye is 10 to the power of -4 watt per square centimeters. And a laser pointer, for example, is allowed to have a maximum of 10 to the power of -2 watt per square centimeter. So a femtosecond laser in comparison has almost 20 orders of magnitude higher intensity. And to understand how the laser radiation is absorbed in a not theoretical material, we have to go from the simplified scheme with ground level and elevated level. We have to go to the band model. So we have the conduction band, which is the blue one, and we have the valence band, which is the green one. And basically, to bring energy in our material, we have to bring electrons from the conduction band into the valence band. And for metals, that's easy. Conduction band and valence band basically touch each other, so we have no gap in between. So photons can be really easily absorbed by the electrons and bring the electrons in the valence band. For semiconductors, it's a little bit harder. We have a band gap of up to 3 electron volts. For example, silicon has a band gap of 1.1 electron volt, and this would mean that we need a photon energy of at least 1.1 electron volts to bridge the gap between conduction band and valence band. For isolators, it's even harder. Aluminium oxide, for example, has a band gap of 9.5 electron volts. And so that you can understand what this means in comparison to some lasers, the CO2 laser has a photon energy of only 0.1 electron volts, So CO2 laser radiation can be easily absorbed by metals, but not by semiconductors. If we use a neodymium YAG laser, for example, metals are no problem, and even some semiconductors can be processed. And the only possibility to process isolators in the 70s and 80s of the last century were the so-called excimer lasers with very short wavelengths, for example, 157 nanometers, because these were the only types of lasers with sufficient high photon energies to bridge those big band gaps. All right, so now we have energy inside of our system. What happens now is dependent on the intensity of the laser beam. If the laser beam has an intensity of around 10 to the power of 4 watt per square centimeters, we are heating the material. So we are generating a heat affected zone. And this is wanted for processes like hardening or generation of tempering colors. If we increase the intensity to 10 to the power of 6 watt per square centimeters, we can even melt the material. Um, you can use melting of material, for example, for soldering or for welding or for cutting. And if we increase the the intensity even further to 10 to the power of 8 watt per square centimeters, the molten material is evaporated and removed from our substrate by evaporation pressures. And this evaporating can be used for laser drilling, for marking, and for special types of laser cutting. And if we increase the intensity even further, above 10 to the power of 8 watt per square centimeters, we are ionizing the evaporated material and we are generating a laser plasma, which again emits photons. Um, that's why you can see the plasma glowing. And in many cases, and plasma is not wanted because you're putting energy inside the already extracted material. Okay, so everything I said in the last few slides was valid for CW and short pulse lasers. So generally speaking, lasers with lower intensity. And now I want to talk about the big advantages of ultra short pulse lasers. And for this, we have to look again at the isolator, a material with a very big band gap, where one single photon couldn't bridge the band gap. And here we can use the so-called nonlinear absorption. And one process of the nonlinear absorption is the multi-photon absorption. And as the name says, one electron not only absorbs a single photon, but in this example, 6 photons IR, or 3 photons green, or 2 photons of blue um, yeah, laser radiation. So with this process of multi-photon absorption, we can bring energy inside of materials with a band gap much higher than the photon energy. And the probability for this process is increasing with increasing intensity. And you saw some slides before, ultra short pulse lasers have the highest intensity. Yeah. And generally speaking, you could say that by ultra short pulse laser processing, the absorption becomes less material dependent. So you can process almost any material and the absorption is generally increasing. And like I said before, by this high peak intensity and the high absorption, we can process, yeah, let's say difficult materials like transparent materials, glass, crystals, or ceramics, which were in the last decades only be yeah, only possible to process with a excimer laser. And the second big advantage of the ultra short pulse lasers is the reduced heat input, because in the short pulse duration, the heat cannot, yeah, dissipate, um, yeah, a long way into the material. So if you look at nanosecond lasers and femtosecond laser pulses, you have almost a factor of 1,000 between the range of the heat affected zone. And therefore we can, yeah, drill holes into material without the formation of burr, or we can cut materials which are very sensitive to heat input, like this match, for example. Um, Now I want to come to some applications of pulsed laser radiation, and we start with the laser cutting. In conventional laser cutting, you're heating the material, you're melting the material, and then the molten material is blown out by compressed gases, compressed air. Um, this is a very efficient laser process, and yeah, has certain advantages. But the big disadvantage is that it's a thermal process, so you have a big heat affected zone, you have material warping, and you have bursts on the upside, on the top and on the bottom. Ultra short pulse laser cutting, on the other hand, here the material is removed by pulsed evaporation of very small quantities. To cut through the material, you have to scan on over your specimen a lot of times, sometimes hundreds of times. And then you can cut through the material. One disadvantage is that we always have a slight taper angle on the walls, but the big advantage is always that we have an almost non-existent heat affected zone, therefore no burrs and really nice cut quality. And we can cut basically every material. Um, Laser drilling is also done by pulsed evaporation. Um, Here you can have a look at basically two different types. Again, the single pulse drilling, where you shoot a single laser pulse on the material, which has a high pulse energy. And with this high pulse energy, we can drill through the material with one single pulse. And the other group of processes is called the multi-pulse drilling. So either on one place, or we have to move the laser beam, and then we are calling it percussion drilling or trepanning or helix drilling. Trepanning and helix drilling is basically laser cutting of very small holes. And the big advantage of the trepanning and helix drilling processes is that we can not only drill round holes, but also square or triangular holes. Um, Next process is the laser coating removal. So you can imagine different technical and decorative yeah, processes where coating has to be removed. And this can be done by two different yeah, ways. The first possibility is to precisely control the ablation depth. This is what we have done in the example on the left side, where we structured this, yeah, these stars on a part of a luxury watch manufacturer. And in this case, we used ultra short pulse laser with a green wavelength. So the ablation depth per pulse was very slow, very low. And by using several hundreds of pulses, we could yeah, control the ablation depth very precisely. The second option is called selective ablation, and this can be done if the coating material has a very low ablation threshold and the substrate has a very high ablation threshold. The last example I want to talk about is DLIP. I think many of you have heard of it, direct laser interference patterning. Basically, you split one laser beam into several subbeams. Those subbeams are superimposed on the sample. By superimposing those subbeams, you get an interference pattern with a very small periodic size. And this intensity distribution is basically imprinted on the sample. And therefore, you can generate surfaces which are, for example, water repellent or have this interesting optical effect. And I want to end my presentation with a quote of the inventor of the laser himself, Theodore Mayman. He said that the laser is a solution looking for a problem. And I hope that with showing you the special properties of laser radiation and a few of the many applications of laser technology, I can give you an idea what he meant by saying that. And I'm happy to answer some questions now.
Thank you, Florian, for your presentation. It was interesting. Let's see if we have questions. So we have hand raised. Not anymore. Okay. Felix Foreman, you have your hand raised. You want to ask something?
Yes.
Yeah.
Thank you for the presentation. I have a question on slide 4.
Mhm.
You said the pump energy, it could be electrical energy, but also optical energy. And my question is, what is optical energy?
Photons, radiation, basically.
Okay.
So the first lasers which were invented, there the laser active was pumped actually optical by what's it's called in English, Blitzlampen, basically broad spectrum lamps which have a high density, and basically all state-of-the-art lasers like the neodymium laser are also pumped optically by laser diodes, actually.
Okay, thank you.
You're welcome, Felix. Let's see if we have another question. So from
Thank you for your presentation. My question is about application of the laser, especially cutting time. Is there any differences between the conventional and USB laser cutting?
There are actually a lot of differences. So we could generally say that for conventional laser cutting, it's much more efficient. So you can cut much faster, but the cut quality is usually better with ultra short pulse lasers. So we have with ultra short pulse lasers less heat affected zones, so no warping of the material. You have no burrs. You can cut transparent materials or heat sensitive materials. Yeah, so it really depends on what you have to do.
Mm-hmm. Yeah, thank you.
Okay, thank you. I don't see anything on the chat, no more hands raised. So if you have any question, meanwhile, you can write in the chat. Florian can try to
sorry.
answer. Yes?
Sorry, can I ask you a question? Yes.
Yeah.
Hi. I would just know if this presentation is shared somewhere, if it's available.
So at the moment, it's not available. Florian, what do you think? We can share this afterwards with the audience?
Yeah,
Okay.
yeah, basically that's possible. Yeah.
So we
Okay,
will
and
share with.
where will we find it?
Yeah, I will take care of that. So I will try to share with everyone that is here after the meeting. So by email
Okay.
or in the share folder, something like that.
Okay. Thank you very much.
No problem. Thank you. So another question, Team
Yes, just one.
Marta? Yeah.
Yes, exactly. First of all, thank you for the presentation. I just had a general question to the interference patterning, and is it possible to do holographic patterning with this kind of technology?
I think maybe Christoph can answer this question better. I'm actually my work is not focused on DLIP. I'm more the direct laser interference, the direct laser writing.
Yeah.
Christoph, can you say something?
Yeah, Florian, I can do. Yeah, basically it's possible. So it depends on what you call holographic patterning. But if it's just about diffracting light and giving you some light diffractive imaging, that's basically possible, and you can play around also with a contrast for this light diffraction. So by changing the size of the interference pattern in each pixel, let's say, you can also give it some contrast. I don't have an example here now, but if you check on our website, there you can find some holographic textures that we produced on stainless steel, for example.
Okay, thank you very much.
Christoph, when you say your website is from our AWS
yeah.
website?
It's the front of
Yeah.
AWS website, yeah. I
Yeah.
can just
Just
put it also into the chat.
Yeah, just to clarify this. Thank you. Okay, let's see if we have more questions. I think not. So yeah, we can finalize this topic. So thank you a lot, Florian, for your presentation and clarification of the questions.